So hello and welcome to the origin of the feature, or unstructured rambling of the compiler engineer. This compiler engineer being me, Paweł Marks. I serve as a release officer for Scala 3, and I am also member of Scala Improvement Proposal Committee, so the committee that steers the development of Scala programming language. And I can talk about programming languages features for hours, but we don't have so much time. And also we need to fit some questions from you here. Speaking about questions, you know the drill. Go to Slido and use passphrase GeeCON. Do it now. Don't wait for the end of my talk. Ask a question whenever that comes to your mind. So I need to structure my thoughts a little bit. And this is what I will be talking about today. First, I will explain what the feature is. Then I will show you the traits of what we can consider good feature. Then we'll talk about some real-life examples of feature of one programming language that was not really perfect. It was not good design. But the idea behind it was sound, so later it was re-implemented to be a really good feature. Then I will show you that reality sometimes is more complex, and then we'll answer some speculative questions, and at the end I will spend a minute or two talking about two letters about which everyone is obliged to talk right now. So, what is a language feature? The first intuitive answer would be that it is something that allows you to write something in one language, but not the other language. But this is false, because all Turing-complete languages are equivalent. If you can do that in one language, you can do it in any other. There is nothing that prevents you to write front-end for your web application in pure C. You are writing it pure C, compiling it to WebAssembly. There are compilers to WebAssembly for C. And then you add some runtime that has access to DOM API, and voila, you have your front-end written in pure C. Also, I don't know if anybody is doing that, but probably you can write hardware drivers using JS. It's only a matter of tooling. But there are some differences between programming languages. One of them, I can think about it, is a boilerplate. Because in different languages, there is different amounts of code required to do the same stuff. So in some languages, you only write one line. In others, to do exactly the same things, you need to write entire, 40 lines long file. We'll see example in a moment. Then there is a matter of safety. Every project has some invariants, some assumptions. Some of these assumptions can be encoded in the code itself, so you can check them automatically during the compilation time. And with other, you have a choice. Either you trust your coworkers that they always know what they are doing, and they will never violate these assumptions and those invariants, or you add runtime checks. And if you have runtime checks, you are sure that these invariants hold, but you may encounter crashes in the production. So it's always better to have more things encoded so they can be checked during the compilation time. So this is safety. Also, we have a guidance. This is something that not much people is talking about, but I like to talk about that. This is how the language is helping you if you don't know exactly what you are doing. So for example, you are a newcomer to the language, or you are just exploring some new API, new library, and see how the language can help you to deal with that. There's also notion of maintainability. This means how easy it is to make change with a project without breaking other working things. And we all know it is interconnected to another aspect that I was talking about before. So the lesser boilerplate we have, the easier it is to make changes, the better guarantees of our programs are, the better safety, the program is easier to maintain, and also guidance also helps with maintainability. You may say that this is a job for libraries. So in every language, we have libraries that are reducing boilerplate, improving safety, giving us some guidance. But you must also remember that libraries are built with blocks that are delivered by the programming language. In other words, The libraries can be only that good as a language is good. And if you have great language, you will have great libraries, but there are no great libraries in bad languages. So let's see some examples. First is about how boilerplate can be different in different languages. When I was last working with Java, it was still Java 8, whenever I tried to have some class holding like 2 pieces of data, immutable data, it looked like this. And now, after Java 14, so for many years right now, you can write something like this. This is exactly the same code. It is doing the same thing, but one is long and boilerplatey, the other is not. But the expressive power is identical. Then we have safety. And as an example for that, I can show you the entire Rust language, because this is the language that is designed as safety, with safety as a first principle. But let me show you something that is, let's say, closer home. So, dependent types in Scala. Let's imagine we have a piece of code like that. Simple class called user. Inside of it, there is nested class called event, and function that is processing incoming event for that user. Simple stuff. Then we'll have another piece of code. Here we are creating 2 users, borrower and lender. We are creating some event for a borrower and sending it to that user for processing. This is ordinary code. It can be done in Java, Kotlin, with only slight syntactic changes. But let's modify it a bit. Let's change the borrower in the last line into lender. And in Scala, this code suddenly stops compiling. Compiler is saying that this is type mismatch. Why? What types are being mismatched here? Let me backtrack a bit and insert the type annotation. You can see that the type of the event is not user.event. It is borrower.event. The type of this event depends on the concrete instance of the borrower. So in this case, this event can be only sent to the borrower, not to the lender. This is great for improving safety, because in big system, there is no way that we can send event to other user that it was supposed to be sent to. And I'm only scratching a surface of this feature. It can be abstracted further. So for example, we can create function that is returning unserved events for some user, and you can see its return type. It is not just a list of events. It is list of events that are dependent on this user U. So this user that was passed as a parameter to this function. So the link to the user is not broken. The compiler is keeping track to what user this event was supposed to go. Then there's guidance, and here I will show you also example from Scala. I think this is my favorite feature of Scala, and it looked like this. We have something called mySequence, and you see some lengthy type, because everything that is after the colon and before the equal sign is a type of this value, and we can unpack it here. So it says this is a sequence of doubles, so sequence of numbers, and it also has member called average that is of type double. And on the right side, in the place of this question marks, we can put anything that satisfies this type. So anything that returns something that is sequence of doubles and also happens to have this average member. And we can use it like that. You can use methods that are in a sequence, so for example, head, and the same way there is no different, you can use this method that you just added to this type. This doesn't seem like super impressive for anyone, I think, but it has hidden power, because normally you wouldn't write that type anywhere. Normally, you would let compiler to infer it for you. And in combination with other features, you can make it really powerful, because Scala compiler can infer those refinements practically from anything, from any data that is known during the compilation time. So let me show you a real-life example, screenshot from the real code, our internal library for dealing with GraphQL. I know it doesn't look exactly like that, but everything that is here in green, you can just treat it as one multi-line string. It is GraphQL query, and it is just ordinary string. But when we use that query and send it to some API, in this case, we are using GitHub API, we receive some response. And this response has this refinement inferred, so actually we are getting code completion for that. In our query, we are asking for repository object, inside of that for issue object, that has 4 fields. And you can see code completions working here. From the result, we can take repository from that issue, and then if we write I, we are getting code completions with 3 fields that are starting with I, because the compiler knows what is the shape of that data. And it not only improves guidance, but also safety. So if we remove something from our query, and we are here only editing a single string in our program, and remove one field, if we have used this field anywhere in our code, we will get a compilation error, because compiler knows that this field is no longer a member of that query. And this is really impressive because it is not downloading any schema from the internet. It is not using any code generation and annotation, magical annotation processing like Lombok or any similar tools. This is just ordinary drop-in library using just the features of the language. And actually, it is really easy to write. During the meetup of Wrocław Scala user group, I was able to re-implement whole core functionality of this library live on stage with explanation, and it took me like 45 minutes. And I believe it is not possible in any other language, another mainstream language, maybe with exception of TypeScript, but I don't know enough about TypeScript to know if it's possible or not. Okay, so we've seen a few examples, and let's now see what traits are making a feature a good feature. I think I subconsciously ranked these traits of good feature from things that are most important for me to the least important, but don't read too much into this. But nevertheless, the most important trait of a good feature is something that I would like to call improvement. If this feature is bringing real improvement to the language. And there are different approaches to that. There is one like harder notion that feature can only be added to the language if it's solving already a problem that is existing already for multiple users or for the large part of the community. I prefer a slightly more lenient version of that I think is more innovative. So that feature is good if it's improved any of these 3 aspects of the language I showed you before for at least some part of the community. But nevertheless, there are lots of feature requests that are features that are not improving much and are only for some small group of use cases. So this can be easily discarded. Then we've got simplicity. Everyone likes to use things that are simple. And by simple, I mean things that have not much moving parts, and also things that don't require you to do lots of works to actually enjoy the benefits of them. This is what we call simple. But the entire notion of simplicity is not simple itself. There's few things that you need to remember about simplicity, and I don't want to go for a long digression or tangent here, so just let me address 2 points. First is that simplicity may come at a price. Let's take an example of memory management in 2 languages, in Rust and in Java. So in Rust, memory management is anything but simple. You need to keep track of lifetimes of every value that you are using. And whenever you violate these lifetimes, so access something after its lifetime ended, the compiler will yell at you. And it will be really frequent. Whenever someone is trying to start their adventure with Rust, they are yelled by the compiler practically constantly. In Java, it is opposite like that. The entirety that is for memory management is just a new keyword. You are just creating objects and you can forget about it. You are sure that when they are no longer needed, the garbage collector will take care of them. But there is a price for that. In Java, it is a big runtime. The Java requires entire virtual machine to run, and this entire virtual machine has quite a long startup time, and also it has a warm-up time. So Java is not well suited for small application that should run instantaneously. On the other hand, Rust runtime is really minimal, and startup of Rust applications can be practically instantaneous. Also, there is a question of performance. I think people are assuming way too much about that because for long-running servers, the throughput of server written in Java and server written in Rust can be really similar. There is not like much difference here. But there is important difference about latency guarantees. So Rust can guarantee practically constant latency, but in case of Java, you will sometimes get the GC spikes, which will cause some requests to be served for much, much longer time than other. So yeah, this is cost that you need to be aware of. But probably in many cases, writing big server that will run for runtime and you are not caring about latency guarantees, you will just choose Java because then it is simple to do. There is also notion of something called false simplicity. There is this quote that I've seen in the internet attributed to many, many famous people, that everything should be simplified as far as this is possible, but not even a tiny bit further. And also my math teacher from middle school was really overusing that quote. But it also applies to programming languages. Sometimes we are striving for simplicity and we are simplifying things so much that actually they become harder to use in the real life, not idealized scenarios. You can see example of that, for many people. It is example of that in Go standard library, in standard library for language Go. And there is a lot of sometimes spicy blog posts written mainly by people writing in Rust that they accuse Go standard library of oversimplifying many things and making it, in fact, harder to use than what is called for them the proper implementation or something that is in Rust. I mean, it is ongoing debate, so you can read those blog posts and have your own opinion about that. But nevertheless, I believe that false simplicity is worse than true complexity. So sometimes we need to stop our urge to hide all the details because the feature might become harder to be used. Then there is trait that I call uniqueness. Uniqueness is a property. It is satisfied when there is only one way of doing one task. So basically, if I want to write something, I know from the start what feature I should use. There shouldn't be like 2 or 3 different language features that I should choose between them. Because then, also, whenever I'm writing and coding in that programming language, there always will be the moment that I need to stop and think what of this feature I should use now. There is a bad example of that, for example, in Scala 3. Because there are 2 ways of declaring algebraic data types. Algebraic data types, you can think of them as something similar to the interfaces that you, from get-go, know what implementation they exactly have. So they have this closed known number of implementation that have. And Scala have 2 ways of declaring them. One, the newer, the more concise and elegant and readable one, is called enums, and the other is sealed traits. And sealed traits are longer, I would say more ugly, but they are more powerful. So 2 times in my career I have a case when I started with enums, but suddenly some requirement changes, and I need to refactor this code into sealed traits. Fortunately, this refactor is really simple, and it only affects the declaration side, not any of the use side. But still, It would be better if I was not forced to do that. So better to have unique features. Then there is discoverability. By that I mean that every time you are reading some snippet of code that have some features that you don't know, you should spot at once that in this code there is a feature that you don't know about. You shouldn't be fooled that your code, that you understand that. If you don't know anything, you should know that exactly, and you should be able to quickly Google that. This is why keywords are great, because whenever you encounter new keyword that you don't know about, you already know that there is something in this code that you don't know how it works, and you can easily Google that. But there is one important thing to remember. Never reuse your keyword. So let me show an example from Kotlin programming language. If you are a Kotlin developer and some junior developer, some newbie, ask you what is a by keyword in Kotlin, in which of this snippet you would think? The first one or the second one? Probably for most of the people, it will be the first one, because this is a feature of the language called property delegation that is widely used by all Kotlin programmers. And yeah, it is a good feature and they know about it. But also there is the other one, which is not as widely known. There's lots of people who don't know about them. And I was once recruiting for Kotlin position. And I mean, I think none of the candidates know about the second snippet. So the interface delegation, it is not really known. And I think the one of reasons which is not really known is because it is hard to find. Whenever something Googles by keyword in Kotlin or even use name of this feature interface delegation in Kotlin, they will probably find results about property delegation. So try to have your features unique in terms of names, in terms of keywords. There is something called composability. So every time you are contemplating adding a new feature for the language, you must think about every other feature and cross-check how your new feature will compose with other features. Because there always will be this one users that will find two most extreme combination of features and try to use them together. Every time. It is guaranteed. And it is completely okay to say that two features don't compose, and when someone is trying to use them together, just throw a compilation error and said it is forbidden. But you need to have good reason for that. And I mean, giving compilation errors that said, yeah, it is possible, but we haven't implemented that in the compiler, or it is not supported in tooling, is not a good reason. So every time you are thinking about adding new feature, think how it composes with the rest of the language. And there is also a question of tooling. Every new feature in the language should have low footprint on a tooling. Because it is not a good feature when it's perfectly supported in the compiler, but it only has partial support in the VS Code plugin, and it has no support at all in IntelliJ plugin, or vice versa. And it's even worse when the linter for the language crashes whenever it encounters files that is using that feature. So then this is not a good feature. Whenever we are proposing something, think about how it can be implemented in tooling, if it's easy to be implemented in tooling. Okay, so these are 6, I would say, traits of good feature. This is what we are using to examine when we're deciding what we want to have in the language. But now let's see some examples. And let's start with the example of something that we call not a great design. I would say this is a bad design. Let me talk about implicit keyword in Scala 2. So in Scala 2, you have something like implicit function. That is implicit conversion here from the integer to the string. So everywhere in your program when you are expecting string, you can now put integer, and this function will be used for conversion. I know implicit conversion are bad, but those were different times when people decided to add that. But implicit keyword can also be added on the parameters. And here we are annotating parameter with implicit, and that means we are not required to pass this parameter always. So we can call this function like that without the second parameter, but only if we have implicit value for that type in our scope. And we are doing it, of course, using implicit keyword. This time, implicit val. We are defining this implicit instance. If we want to define something that is called conditional implicit, so some implicit value that is only present if some other implicit value is also present in the scope, we are using something that looks like this. So this is implicit function that is taking implicit parameters. And you probably already see a problem here, because this last feature, I would say it's kind of good, kind of okay. There is needed sometimes, but it looks pretty much exactly the same as the first snippet. So the implicit conversion that is evil. And it is really easy to confuse about them. And if you don't know Scala exactly, Scala 2, I mean, you are often confusing them and don't know if what they are doing here is declaring some implicit conversion of creating some conditional implicit or whatever. And then there is also something called implicit class. This was the preferred way of adding extension to types in Scala 2. So basically you are creating this class called average list in this example that have method double, and every instance of list of doubles were implicitly treated as it was instance of this average list. So you are having this extension called average on every list. Yeah, this is how it was done in Scala 2. 9 years ago, my friend told me that he hates reading Scala code, that he really despises it. I asked him why. He said, because all of this implicit. And I asked him, which implicit? Implicit conversions, implicit parameters, implicit value, conditional implicit classes? And he was, for a moment, shocked and then asked me, so there is a difference between them? I just hate them in general. Yes, seeing something like this, when one keyword is used for many different concepts, you can hate that feature, or all these features. There is a reason for them to be using the same keyword, because under the hood in the compiler, they are actually using the same mechanisms. And sometimes it helps with composition, and sometimes it's also super misleading. But this is not good from user perspective, because for the users, those are different things used for different things, and they shouldn't be so similar to each other. But the idea behind it was actually good, and it was completely re-implemented in Scala 3. So what was the idea? Let me show you an example. We have a method that is downloading user data. And in any other programming language, it usually would have two parameters. One is ID of user that the data we want to download. The other is connection to the database. But those two parameters are completely different from the point of view of person that is calling that function. Because one of them is, yeah, it is input. This is something that they own, something that they manage, something that they take care of. So this is the ID of the user. And probably they will assume the same about what this function returns. But the other, connection to the database, they don't care about managing that stuff. They just want to assume that in their scope they have some connection and they can use it. And this is the separation of inputs, and I would call it environments, is present in Scala 3. In Scala 3 you are saying that you have method download user data that have input in form of ID, and is using a connection. This connection is a type, and you are saying that this way, that this function can be only called in scopes in which you are sure you have this connection in the environment. For example, like this. You have other function that assumes to have connection and display in its environment. So the compiler knows that it is safe to call download user data here, and you don't need to care about connection. It is in your environment. Otherwise, if the connection was not here, this will be, or any other enclosing scope, this will be a compilation error, because you cannot connect to database from here. But from here, it is okay. There is also a way if you want to manage the connections by hand, because some part of application will need to do that. And to add this connection to the environment, you are using given keyword. So we have dedicated keyword that is declaring what is the given instance of the connection. And if you want to make it conditional, like conditional implicit in Scala 2, so for example, you can want to say that there is connection to the database in every scope that contains some DB context, something called DB context, you can write it like that. You are creating given connection that is using DB context. So I think this way, when you have separate keywords that are saying what you want to do, it is much better, much more readable, and you can easily find information what this function is doing. You may have realized that there were two more things that implicit keyword was used for in Scala 2, one of them being extension methods. And for extension methods, we just now have extension keyword. Because if you want to declare an extension method, just write it. This is an extension, and the type you are extending. It can be that simple. And there were also other feature, the implicit conversion, but we do not talk about implicit conversion in Scala 3. Okay, but I need to say that sometimes reality is much more complex. So you cannot just take any of this feature, let's say, using keyword in Scala, and take the 6 traits of good feature and rank this feature using them. So for example, you cannot say that using keyword is like 9 in discoverability, 8 in improvement, because it is not as simple as that. It is much more going on. So for example, there is a question of something called intuitiveness. I tried to not to use word intuitive, even though it is really often used in the case of language features or language development. We used to say a lot that in this language it is much more intuitive than the other. But what does it even mean? Let me show you. Function foral from Scala standard library that is taking a list and some predicate, and it is saying this predicate is satisfied for every element of this list, of this collection. So of course, in the first line, we will have like 4 elements, and we are checking if every one of them is greater than 5. It is false, we have 1 and 4. In the second example, every of the elements is greater, so we are returning true. But what this method should return for empty list? I mean, probably most of you will answer obviously true, because this is how this method behaves. This is how counterparts of this method in Java, Kotlin behave, and this is what is in mathematical logic. It's like general quantifier, so for no elements, it is also satisfied. So this will be a true. But at least once, I've seen someone who claimed for the Kotlin counterpart of this method that this is a, and I quote here, a known bug in the standard library that this method is returning true for empty list. Because for them, it would be intuitive, it is returning false. Probably, they may have come from some front-end background, because I've seen one front-end library. I think it was something to deal with event streams. When you are checking if every element in this stream was satisfying some predicate, it would return false for empty stream. Why? Because the authors of this library realized that in every case, in every example, whenever they are using it, they need to check if the stream is not empty and special case that. So they thought it will be easier to include the special case in the method itself. And of course, it is documented. It is not intuitive for some people. But for people that are used to that library, this is the intuitive way. And probably when someone like that comes to Kotlin or Scala and see that we are doing things differently, it will be not intuitive for them. You may argue with them that we are right because like logic, but still, it will not be intuitive for them. So you need to think about to which people you address your feature, to which it is supposed to be used by, to know which can be intuitive and which can be not intuitive for them. Then there is a question, is there always correct solution? Because back up till now, I was constantly talking in absolutes, so this is better, this is worse. But there are cases when this is not obvious. So let's talk about type systems. Years ago, there is this discussion between statically typed languages and dynamically typed languages. So one of them when you get type errors in the compile time, the other when you get it in runtime. Statically typed languages have won practically most of the niches except some few isolated, I mean big niches, when Python is dominant, but Python still has type hints. The statically typed languages are ruling everywhere. And even more, if 10 years ago somebody told me that in the front end, the dominant language will be statically typed, I wouldn't believe them. But it is the reality right now. So we are no longer talking about static versus dynamically typed languages. Now we'll be talking about only statically typed languages. So all the compilation or the type errors are during the compilation. But on one of the spectrum, we have structural typing, and on the other, we have nominal typing. The structural typing means that it is a duck if it quacks like a duck. In nominal typing, it is a duck if it implements the interface that duck was supposed to implement. Yeah, the nominal systems are probably for what most of us are working with. But I really need to say that the structural typing with this approach of if it's a duck, if it quacks like a duck, are much more intuitive. And let me show you. If we have some interface for person and class for car, defined like this, pretty ordinary, let me introduce to my neighbor who is 20 years old Volkswagen Passat. Okay. So, as I said, we are used to nominal type system. Kotlin, Java are 100% nominal type systems. Then there is Scala, which is nominally nominal, but has some features of structured type languages. So, for example, these refined types I showed you before, they are parts of something closer to structural typing. There is one really interesting language called Pony, which has both entire structural type system and entire nominal type system at the same time in the same language. I don't know about any languages that are mainly structural but have some nominal features in it. Let me know in a question if you know about any language like that. But there's also fully structural TypeScript. And this example with my neighbor being Volkswagen was 100% correct compiling TypeScript. So here you can see that these languages have different use cases. Because of this example I showed you before, I probably wouldn't use structurally typed languages for the big projects that are developed and maintained for many years for many developers. Because it is so easy to make a mistake and implement some interface by accident where you are not really obeying the contract of this interface. Because some things in the interface can be encoded in types in the names, but the other cannot be. So sometimes you have the correct type, correct name, but you implemented this interface by accident. So this is why I would prefer for such kind of projects nominally typed languages. But for things when you need to vaguely define the shape of your data and still have it be checked during the compilation time, because TypeScript is checked during the compilation time. And also, you are interacting, for example, with multiple external APIs, like lots of front-end applications. The TypeScript is an excellent choice for you. So for these use cases, the TypeScript would be better. So we have an entire spectrum of type systems, and for some use cases, one are better, for other, the other. So we must say that this is not true that the correct solution and the correct choice always exist. Then there is something completely from the other side. So the question, is language evolution convergent? We can see sometimes convergence in language evolution. My favorite example is Kotlin and Scala. Scala, I showed you before, has this contextual abstractions, when you can have assumed that something is in your environment and you are not caring about handling that, it is just passed to you. And Kotlin has the same feature accidentally, because they have something called extension functions. And these extension functions in their type, it is great choice, by the way, by the Kotlin compiler team. The type of the receiver is part of the type of the function. So you can have lambdas that you are assuming has some receivers, and they are using function accepting such lambdas to have some scopes in which some things are known to be in the environment, but you are not really interacting with them directly. It is great for DSLs, and this was not the intended use for the extension methods, but the Kotlin compiler team acknowledged that people are using it like that and embrace it. And they added multiple ways to make it easier. So for example, right now they are prototyping unlimited number of context receivers on the functions. So we are no longer limited to the lex. I don't remember how they called, but you only can have 2 receivers. But they are experimenting with making them unlimited. So it will be much easier to achieve something that is similar to what you are doing in Scala, in completely different language that was not designed in mind. But people just started to using like that, and the evolution of languages converged. So now is the question, is every new idea in programming just another rehash of what was known before? And the answer is yes, it is. For every new exciting feature in any language, I can guarantee you that you will find like Lisp dialect from 70s that already has that feature, but this dialect is forgotten, and you will not find anywhere any working compiler for that. But it was there. Also, every feature that is now being added to the language is somewhere in some academic paper from years and years ago. And features that are being added right now were studied probably in the 90s or even before that. So if you want to look for innovativeness, innovations, don't go to the mainstream languages because they are just rehashes of those known before. You can maybe go to the research languages. One of my favorite examples is something really clever that is called Effect with K. Go search that out. Or even better, go to research paper if you are ready to read them. And there is a lot of innovation happening right now. So for example, right now at EPFL, the team of Professor Martin Oderski is working on something called capture calculus. And this is something completely new, and they are prototyping that and thinking about it in the future as a future addition to the possibly Scala language. We will see. Go search that out. It is really interesting. And the last question here is, will we ever have one perfect programming language fitting all our needs? I don't believe so, because as I showed you, sometimes you have completely incompatible needs. So there will be different languages for that. But I believe there are some niches already, which one language took the biggest portion of the pie, that they are dominating in this niche. So for example, in machine learning, it is practically only Python right now. In front end, the TypeScript is starting to be dominating. And I believe in the future we'll have more niches like that. Maybe even in the future we'll have one standardized backend language. Who knows? And now I will talk a few sentences about these 2 infamous letters, so AI. I am not AI researcher, I'm not even close to AI researchers, so I will not talk about long terms and if AI will take your job or not. But I'm using AI assistance a lot, and I'm enjoying it. But I see that while it is improvement in my performance, how I can work, there were other things that were much greater boost for my productivity before. So for example, years ago, switching in one project from Java 8 to Kotlin was much bigger productivity boost than using AI assistance can be now. So probably, if you are benefiting a lot from the AI, like a lot, probably you are working on the wrong level of abstraction. Probably the tools you are using are too fine-grained to the problems you are solving, and you require too much boilerplate to deal with them. And AI is perfect in generating boilerplate, absolutely perfect. And this is why I think from this free aspect I showed you at the beginning, boilerplate will not be that important in the future because we have AI to generate that. But I think the two others of them, so safety and guidance, will be even more important. Because unless something like big revolution happens, and I'm not saying here about upgrades like upgrades from GPT-3 to GPT-4, AI will make mistakes. And if you are operating on high level of abstraction, if your code is doing hard things, the AI will make mistakes and is making mistakes constantly. And this is why you have tools that allow you to not only test automatically. So for example, in the compilation time, if your code makes sense, if it's holding your guarantees, but also show you the way how you can fix it. So this is why I think the guidance and the safety will be even more prominent and even more important in the future. That's all. Thank you. I will look for questions. What's the best reason to go into Scala in 2023? There is lots and lots of feature in Scala. I only wanted to show you like 2 small peaks. One of them is, I think that it allows you to create libraries that are on safety level that is not possible in any other language, especially if safety is important for you. You can check during the compilation time things that are not possible to check in another language. And actually in 2023, Scala has not so steep learning curve as it has before. I mean, starting a simple project right now in Scala is much easier, much less hassle than in Kotlin or Java. I know it's hard to believe because Scala, in the years of Scala 2, was quite infamous for that. But right now, it is pretty much easy. And you have not a very steep learning curve. I would say it is actually quite flat. And you have powerful features waiting for you to be discovered. And you can write much, much safer code than in other JVM languages. So this is like from top of my head here. Next question is Objective-C. I believe is structural by design, but has some. Oh, I haven't known about it. So noted. I was never using Objective-C. So yeah, so good to know about that. What is the feature in Java that you dislike the most? Oh, it was many years since I stopped doing any serious coding in Java. And what I really dislike there, I mean, probably, oh, I know, there's one pet peeve of mine, that in any other language, there is either it is as easy to define something to be immutable as it is define it to be mutable, or even it is harder to make it mutable. So for example, in Rust, if you are using let, it is immutable, you must write mut let for it to be immutable. In Kotlin and Scala, you have val and var, which is at the same level. But in Java, if you are using var, to make it immutable, you must go this one step further and write final var. So actually, language is actively punishing you for trying to make it safer. This is one thing I really, really dislike in Java. Others being probably this, that mutability is a default. I mean, mutability is needed in the language, especially in the compiler. We are using a lot of mutability. Compiler is nowhere near immutable code, but it always, you should be aware when you're opening something for mutation. And in Java, it is always done implicitly. So this is something that I know why they took this design approach, but I don't think it's a good design approach. Okay, so thank you all, and see ya. If you want to chat with me, I will be near the software mill stand. You can find me here. Thank you.